AI adoption often focuses on making specific departments smarter, but true operational leverage comes from making the entire enterprise system conscious. Most organizations start by integrating highly capable models into individual workflows. DevOps uses AI for monitoring, while product teams and developers rely on AI-based copilots. Despite the investment, release cycles often remain stalled. Even with smarter tools, leadership struggles to see the systemic ROI they expected because the AI-generated insights aren't operationalized. This is the intelligence in pockets problem. You have pockets of localized speed, but because the nodes don't communicate, the overall system remains blind to the data moving through it. The enterprise lacks a shared intelligence graph to link these functions. There are no synchronized escalation models or learning loops that allow one department to benefit from the signals of another. Without this cross-module synchronization, AI remains an ornamental layer, a tool added to a system rather than an architecture that makes the system work. History shows a consistent failure pattern in major transformations. Whether it's agile, lean, or digital adoption, they all eventually hit a bottleneck. This is the sedimentation trap. It starts with a clear objective, but over time, manual audit points accumulate until governance weighs down the operation. Agile became ceremonies without value. Lean became auditing forms. Compliance replaced clarity. Using AI within these legacy workflows creates intelligent chaos. You gain speed in the tools, but without a new way to handle accountability, the governance debt grows even faster. Traditional governance depends on humans manually creating artifacts, filling out registers, and auditing logs. An AI-native foundation requires an architecture where these artifacts are generated automatically by the system. Solving AI risk requires moving past manual review boards and into an architecture where anti-sedimentation checks are a structural requirement of every data event. Implementing this starts at Layer 1 of the AENA framework, the data definition layer. We can look to the work of Carolus Linnaeus for a historical parallel. Before his work in the 18th century, the study of biology was fragmentary and inconsistent. This title page from Systema Naturae represents the intellectual contribution that changed the field. Linnaeus didn't create the animals, he built the classification schema that made systematic study and prediction possible. Organizations face the same challenge. Decisions, policies, and review cycles already exist, but without a shared classification system, they remain unstructured and invisible to AI. This is where we apply the Data Event Taxonomy and Response Model, or DTERM. It provides a classification schema that makes automated scoring, routing, and posture detection possible. Building smarter AI on top of unclassified signals only amplifies ambiguity. Raw signals must be categorized at the bedrock layer before the system can act on them. This grid shows the 4 dimensions of the DETRM classification schema. Every piece of enterprise data is categorized through these quadrants. The decision marker, or D, captures data that influences an action. This provides the traceability needed for accountability, tagging risk scores, architectural choices, and resolution decisions. The enforcement marker, E, identifies boundaries and policy rules. It tracks things like SLA breach flags, security anomalies, and audit events that show when an agent's scope was overwritten. For long-term pattern recognition, we use the trend marker, T. This monitors joint metrics like velocity and quality drift, tracking MTTR and the overall utilization quality index. Finally, the review marker, R, flags signals that require human contextual evaluation, such as ambiguous edge cases or specific anti-sedimentation audits. By categorizing every raw data event into these dimensions, the system converts unstructured noise into a routable operational state. To see how this works in practice, we can look at structured data from a tool like Jira. When the system reads the ticket fields, like issue type and component, it assigns a decision tag and a confidence score without needing to interpret free text. This D tag then auto-populates the decision register. It pulls the summary and the ticket assignee directly from the data, establishing an owner and a rationale for the record. This triggers Layer 2, the agentic orchestration layer, which determines how that decision moves through the system. Every handshake is documented as the system follows a defined escalation path, starting with deterministic rules, moving to NLP, then to agentic intelligence, and finally to human review. Because the metadata is classified at the root, governance artifacts write themselves. This completely eliminates the massive manual data entry work that usually causes these complex transformation systems to ultimately fail. Layer 3 is the system application layer. This is the environment where AI executes tasks within defined process contexts. If the system detects a fault or an exception during execution, it triggers the autonomous complaint engine. This engine generates a structured fault event. The payload calculates root cause probability, business impact, and remediation confidence. The system then selects a predictable healing path, such as a rollback or patch, to mitigate the fault via predefined contracts. Every one of these exceptions is permanently logged in the Resilience Trace Log, or RTL. The RTL ensures that operational friction isn't just a resolved ticket, it becomes a structured data point used to build the organization's institutional memory. The final layer of the architecture is Layer 4, the Adaptive Intelligence layer, which enables the system to self-improve. The system analyzes the resilience trace log to find dense clusters of recurring fault patterns. When it identifies a frequent pattern, it extracts a candidate rule, a specific proposed adjustment to the system's logic. This candidate rule is sent to a human overseer, who reviews the pattern and grants approval. Once approved, the rule feeds back into Layer 1, updating the DETRM classifier, so the system can handle the issue autonomously the next time it occurs. This closed learning loop is what defines a conscious system. It converts static compliance data into self-healing, compounding intelligence. This architecture requires humans to shift their focus from manual data production toward architectural oversight. This involves specific mandates for operators like the Workflow Step Orchestrator and the Agent Skill Definer, who manage the boundaries of the system. The human role becomes one of confirming and correcting the rules the system generates, rather than creating every record from scratch. The Detromena framework provides the structural standards required for AI-native enterprises, aiming to reach the same level of architectural rigor found in established industry frameworks. Deploying capable AI models without this level of architectural synchronization leads to unmanageable chaos as the business scales. To build a truly conscious enterprise, the structure of the system must precede the scale of the deployment. Classification is the prerequisite for capability.